The basic feature of a hyperbola that generates the formula for a hyperbola, kind of like an ellipse, is this relationship between a point on the curve and the distance between that point and the two foci. So as I move this point, the relationship is not that the sum is exactly the same, which would be the ellipse, but actually it's the difference of these distance that remains the same. So here the constant is 1.18. So no matter where I move that point, that number is always going to be 1.18. So that would generate the idea of how to come up with the formula or equation of a hyperbola. And a hyperbola is similar to an ellipse, that it has an A, B, and a C, where the C represents the foci, but A and B get a little bit different treatment. Alright, so to continue on with our topic of hyperbola, I just want to tie in the ellipse and the hyperbola together because they're very, very similar in a lot of different ways. If we went about and did the distance formula, subtracted the distance and set it equal to a constant number, and went through all the algebra like I did with the ellipse, we'd eventually end up at this formula where the substitution b squared is equal to c squared minus a squared was used. So under all that algebra, we would have ended up with c squared minus a squared, and we would turn around and just call it b squared. And then b becomes part of our graph. To simplify this more, we're usually looking for the foci, which is c. So this would be c squared equals a squared plus b squared. So it looks exactly like the Pythagorean theorem. So the way to keep these two straight, c squared equals a squared minus b squared, and this one, I use this little trick. With the hyperbola, between the two fractions is always going to be a minus. So it's either going to be x squared minus y squared or y squared minus x squared. And that'll change the direction that the hyperbola is facing. The ellipse, on the other hand, uses a and b to change the way it faces. So when the hyperbola is minus, the focus formula is going to have the plus. With the ellipse, it's plus in here, and its formula for the focus has a minus there. So they're always going to be opposite of one another. Alright, so let's do a simple example. X squared over 1. You can just write it as x squared, but I like having that number down below so I can see what's going on. Minus y squared over 3 is equal to 1. So unlike the ellipses, where a had to be the bigger number, because it was always a squared minus b squared, and if we picked the other way around, you'd end up with a negative, and it just doesn't work out really well. In this case, though, because it's a squared plus b squared, it really doesn't matter. So the focus is going to be who's under the first term. So here, this is x squared. Whatever is underneath it, it's going to be a squared. So here we have a squared is equal to 1. Over here, this must be b squared is equal to 3. Thus, a is equal to 1, and b is equal to the square root of 3. So what we're interested in is where are the foci. So let's substitute in what we have. We have a squared is equal to 1, so this is going to be c squared is equal to 1, and b squared is equal to 3, so we're going to substitute in for b squared is 3. So we're going to get c squared is equal to 4, so we're going to come down here and square root it, and we're going to get 2. Now technically it's plus or minus 2. Same thing for the b, it's plus or minus the square root of 3, and plus or minus 1. But I usually take care of that part in the graph. Alright, so this thing is going to be centered at the origin, and everything's going to move away from it. Because the a is underneath x, it's going to go left and right. So this becomes a vertex, or these two become the vertex of this hyperbola. C is equal to 2 is going to go along with that first letter. So if the first letter here is x, we're going to move the foci along the x-axis. If we flipped it around and had y squared minus x squared, then we would move the vertices and the foci vertically. But in this case, everything's on the horizontal, so we're going to go I'll do this in green because they're not part of the graph. Here's foci 1, and here's foci 2. 2 to the left, 2 to the right. All right, so B in this case is not one of the vertices like it is with the ellipse. It's a minor vertice. In this case, B just becomes part of something else. So I'm going to have to talk about a little bit higher level math and some reasoning. So let's do this in purple. If I solve this equation up here for y, actually let's go right to the top. Let's solve this one for y. We're going to get y squared plus 1 is equal to x squared. And if we get rid of the fractions, let's see, that would make this bx squared, or b squared x squared. And over here you would have, oh, I messed up. Okay. To figure out what the b is doing is a little bit more complex. So let's take this equation up here and start solving it for y. So if I start solving it for y, the first thing I would do is multiply through by the common denominator, which is a squared b squared. So this will give us b squared x squared minus a squared y squared is equal to a squared b squared. All right, and then what I'm going to do is a flip-flop of these two, and it changes the sign appropriately. So I'm eventually going to get y squared is equal to, let's see here, we're going to divide by a squared, so this is going to become b squared over a squared x squared, and then it'll be minus b squared. And let's just go one more step. We're going to let x and y both get really, really big. There's a little bit more detail to it, but this will make things a little bit easier. So as x get really, really big, x and y get really, really big, huge, billions, trillions, gazillions, these two terms keep getting bigger and bigger and bigger. But this term, all by his lonesome over here, stays fixed. So as the other ones are getting bigger and bigger, this number stays fixed, and therefore it becomes known as irrelevant. It's kind of like if you're a billionaire and you take away a couple $100s, the billionaire is really not going to notice it that much. So it becomes known as irrelevant, inconsequential. So basically we can just say, oh, let's just ignore this for a second because x and y are getting really, really big. Well, if we can ignore that one term, then we can take the square root of both sides, and we're going to get y is equal to plus or minus b over a x. And what that becomes is a line, also known as an asymptote. What the graph will approach as x and y get bigger and bigger and bigger. So this asymptote tells us that the slope is going to be b over a. All right, so here's b, square root of 3. Here's a as 1, so the slope is going to be up square root of 3 and over 1. Well, square root of 3, let's see here, need an approximation, is 1.7-ish. So the slope here would be 1.7 up, so right about there, and over 1. So we'll be talking about this slope through the origin. And then also, if we go 1 to the left and down 1.7, we'd be over here. All right, but we also have this minus to contend with. So it could also be, I should be doing these in a different color. Let's do red. It could also be the negative of this slope. So we're going to have a line going through these three, and we're also going to have a line going 1.7 up and back 1, and 1.7 and forward 1, down 1.7 and forward 1. And what this creates is this little rectangle. So I'm going to connect my little dots. And this is what you would do on a piece of graph paper. You wouldn't really need the equation of the line, but it kind of gives you an idea of what's going on. And these two asymptotes, let's see if I can draw this in. See if I can get lucky. Would be going here. Oops. Here. So that would be one of the asymptotes. And this would be the other. Oops, I let go of it. You just go right through the corners of these boxes. So those are our slope points. There we go. And these become asymptotes for the graph. So as I draw my graph, the graph has to get closer and closer to this blue X. All right, so let's draw my graph in here. I'll do it in orange. These are vertices, so these are parts of my graph. So these two I'm going to darken in a little bit more. And the curve is going to leave this point, never get inside this red box, come along that blue curve, and then come along, that blue line. So it approaches, let's make it thicker, cover up my mistakes. So it'll approach this line. This is really hard to draw this way. And this line. And then over here it's going to approach this asymptote and this asymptote. So the orange part of this whole picture is the graph of x squared over 1 minus y squared over 3 is equal to 1. All right. So here's a computer-generated version of the graph x squared over 1 minus y squared over 3 is equal to 1. And you'll notice that mine got really close to this dotted line quickly, but that b squared that I kind of made irrelevant does affect it close in. It's just as we get further and further away, the blue graph is going to start approaching the green dotted line much, much closer as x and y get really, really big. So another way of graphing this, rather than dealing with the equation of the line, is actually kind of simple. Let me grab some points here. You would do the A, B, and C, the A and the B measurements on the graph just like you would an ellipse. So in other words here, A was equal to 1, so you go 1 to the left and 1 to the right and plot those 2 points. Now B was equal to 1.7, which is right here. So you would plot this point, and you would go down 1.7 and plot that point. The only difference is, instead of drawing an ellipse through these points, you're going to draw a rectangle through these points, and then through the corners, you're going to draw these asymptotes. And then the only confusing part is whether the ellipse is going to go this way, and that only happens if y squared is in the lead of this equation over here, or as it is now, the x squared going through that point. Now one thing I did not graph on this were the foci, but they should be here at -2 and +2. I can put them back in. So there's focus 1 and there's focus 2. And this would be the graph of x squared over 1 minus y squared over 3 equals 1. If you had a graphing program, it makes it look a lot prettier than what you can do by hand. So let's try another example, and I'll go through all the details that are possible. So here we have y minus 2 all squared over 9 minus x squared over 4 is equal to 1. Because of the minus, we know this thing is a hyperbola. But the center of the hyperbola is changed. So the x is not changing in its direction for the center. So the center for the x is still 0 because there's no number next to it. But the y has been moved up 2. So this graph is going to have a center of 2, 0. Well, that'll be fine, blue. All right, so what I generally try to do is write in any imaginary axes that are necessary. So one of the imaginary axes is going to go along the line y equals 2. And that'll just help me keep things a little bit straight. That's a little high. Let's see if I can drag it down. fix it that way. All right, so we have this imaginary axis there, and then we're going to keep the y-axis as the other one. All right, so the rest of it is this. Underneath the first term is always going to be a, so in this case, a squared is equal to 9. That leaves b squared is equal to 4. And then we can find out what c squared is by using the formula c squared equals a squared plus b squared. And then plug in what we know. So c squared is equal to a squared, which is 9, plus b squared, which is 4. So c is going to be the square root of 13 plus or minus. And we get that. So if we break this down, we're also going to get a is equal to plus or minus 3, and b is equal to plus or minus 4. All right. So from the center point here, the a is telling us to go 3 away from it in the direction of y, so vertically. So these are going to be the vertices of my graph. So it's going to be 3 up, and that'll actually be a point on the graph, and 3 down. Now my graph's not going to look very pretty at the top part, so I'll focus on this bottom part. The b, on the other hand, is just imaginary points. So I'll color them in yellow. Try to stay away from the idea that they're part of my graph. So b from the center point is going to be 4 to the left and 4 to the right. But these are not points on my graph. But they're going to give me that nice little rectangle that I can draw my asymptotes through. So if I draw my rectangle, between all these 4 points, don't connect them with straight lines, you'll get a diamond. This becomes my asymptote rectangle, what I can generate my asymptotes from. Okay, so let's see. If I draw in my asymptotes, let's try orange. We would start at this point, go in this direction, off and forever, and then do the same thing going the other way. Ooh, that's good enough. And then this way. And this way. Alright, so these become the asymptotes of my graph as it goes through these 2 points. Oops. These 2 points. So this is a vertex, and this is a vertex. So as I draw my graph, it's going to have to get close to these asymptotes. So let's make it thick again, and go this way, and this way, and then from here it's going to go up. But I'm running out of room. So this would be the graph. The blue part of it is the graph of this ellipse over here. The only thing I haven't plotted is the square root of 13. So to get the foci in there, the square root of 13 is 3.6, approximately, give or take a little bit. So 3.6 approximately. So when I plot them in here, we're going to start at the center and go 1, 2, 3.6. It's someplace around here. Let's make it red, because again, it's not part of the graph, it defines the graph. 1, 2, 3.6. And the coordinate of this point precisely is going to be, the x-coordinate is 0, because we're still on the y-axis here. And the y-coordinate is going to be 2, because that's where it started from. And then we went down square root of 13. And therefore, when we go up, which I'm not going to be able to get it in there, 3.6, yeah, right about there. This coordinate is going to be 0, 2, and I went up square root of 13 from the 2 coordinate. And those would be the precise foci. Call that one F1, call that one F2. It really doesn't matter which one you call which. And that would be the absolute complete graph of this hyperbola.